Lesson 9, Interpreting Exponential Functions. Let's find some meaningful ways to represent exponential functions. 9.1, Equivalent or not. Lynn and Diego are discussing two expressions, x squared and 2 to the x power. Lynn says, I think the two expressions are equivalent. Diego says, I think the two expressions are only equal for some values of x. Do you agree with either of them? Explain or show your reasoning. So let's try a table first. As you can see, we have x. We're going to try out some different values. And then here we have the two expressions, x squared and 2 to the x power. And then this column, we can answer whether they are equivalent or not. So I've gone ahead and whenever I randomly choose values of x to try out in a table, I usually always go with -2, -1, 0, 1, 2. That's always a safe place to start. So as you can see, for x squared, -2 squared, negative times negative is positive, so we get 4. 2 to the x power, 2 to the -2nd power is really the reciprocal of the positive power, 1 over 2 squared, which is 1/4. Are 1/4 and 4 equivalent? No, they're not. Let's try the next x value, which is -1. So when we plug in -1 squared, we get +1. And 2 to the -1st power is really 1/2. And these are also not equivalent. Let's try 0. 0 squared is really just 0. 2 to the 0 power. As you remember, anything to the 0 power is equal to 1. And again, these are not equivalent. Let's try +1. 1 squared is 1, and 2 to the 1st power is 2. Still not equivalent. Let's try 2 squared is 4, and when we substitute 2 in for x, we also get 2 squared. So naturally, these are equivalent. Okay, so how might we get the complete answer here in case there's more than one value of x that makes these two expressions equivalent? We can use our graphing calculator. So here we have our graphing calculator with x squared plugged in and 2 to the x power plugged in for y2. And when we graph this, we see that we have a few points of intersection. Let's take a look at the table. And let's go back down to 0. As we can see, they should look familiar, and we stopped right around 2. We can see that when x is 2, both y values are equal to 4. So we have a match there. And as you can see, there's another x value that gives us equivalent expressions or equivalent values, and that is 4 gives us 16 and also 16. So 2 to the 4th power is 16 and 4 to the 2nd power is 16. 9.2, the cost of solar cells. The cost in dollars to produce 1 watt of solar energy is a function of the number of years since 1977 T. From 1977 to 1987, the cost could be modeled by an exponential function f. Here's the graph of the function. So as we see, it's definitely decreasing as time goes on. So it means that the cost, the y-axis here is labeled the dollars per watt. The cost is going down, and that makes sense because as technology increases over the years, we figured out how to create solar energy cheaper and more efficiently. Number 1, what is the statement f of 9? And these two squiggly lines, that's not an equal sign. You would say this approximately. What is the statement f of 9 is approximately 6 saying about this situation? You could also say is about. So if we look closely, we can find that 9 years is right here. F of 9 is about 6, because here we're going by 5s, 5, 10, 15, 20. So it means that 9 years since 1977, in other words, 1986, right? Because remember the x-axis means the years since 1977. So if we're talking about 9 plus 1977 is 1986. So in 1986, it costs about $6 per watt of solar energy. That's how you would interpret this statement here. So in this lesson, we're really we're bringing back the function notation, the whole concept of functions as input and output. So let's look at number 2. What is f of 4? What about f of 3.5? What do these values represent in this context? Well, f of 4, if we go to 4, we know that's 4 years after 1977, so that's 1981. So in 1981, the cost of 1 watt of solar energy is right about 25, maybe 26. And there we go. So f of 4 means it costs about $26 per watt at the start of 1981. Now how about 3.5? F of 3.5, so here's 3 and here's 3.5 years. So we're not going to be exactly at the start of a year, but we'll be 6 months through or halfway through a year. So f of 3.5 means it costs about $29. We go up to here, we say that's, this is about 30, so just a little under is $29 per watt halfway through 1980. Number 3, when f of t equals 45, what is t? So here we're going to work backwards. They give us the output. The output is $45. Find t. Find the number of years after 1977 that the cost per watt is about $45. So if we look at $45, here we have 40, here's 50, here's $45. And we go over to the graph, we see that it hits exactly at 2 years. So the answer is 2. T equals 2, which means 2 years since 1977, or in 1979, it costs about $45 per watt. Number 4, by what factor did the cost of solar cells change each year? If you get stuck, consider creating a table. Well, I'm not going to get stuck. I'm just going to go ahead and create a table right away. So here's my table. I've labeled it years since 1977 and cost per watt. This would be my input column and my output column. And I've really just gone through and written down all the ordered pairs that I see here. So I know at the very beginning, at 0, it's going to cost $80 per watt. And then at 1 year, it's about $60 per watt, and so on and so forth. For, as you can see, our table looks like this. And we don't have to do every single point on the graph, just the first few. I did 0, 1, 2, 3, 4. And now what I'm going to do here is I'm going to, because we're talking about factor, right? By what factor did the cost of solar cells change each year? I need to divide, because when I divide, I can figure out, well, how much am I multiplying each year to get to the next value? I can see clearly that we are decreasing, so the factor must be a number less than 1, right? Exponential decay. So what I've done over here is I've divided. 60 divided by 80 is 0.75. And here's the rest of them. 45 divided by 60 is about is exactly 0.75. And 34 divided by 45, I'm starting to get numbers slightly different than 0.75. Here we have 0.75 repeating. And that's because down over here where we have 34 and 26, we're sort of estimating, because it's not exactly on the horizontal and vertical guidelines, it's a little below, so I'm estimating. And that's why we're slightly off. So as you can see, 26 divided by 34 is 0.7647. So the factor, it's safe to say that the factor is 0.75. You may also say 75%, and you may also say 3/4, right? So this is clearly less than 1, and that's why it is exponential decay. Point 3, paper folding. The thickness T in millimeters of a folded sheet of paper after it is folded n times is given by the equation T equals 0.05 times 2 to the n power. What does the number 0.05 represent in the equation? Well, hopefully by now you are quite accustomed to the general form of an exponential equation. Here's the starting value, and here's the factor of change, or the common ratio. And here we have the input, and here we have the output. So to the n power, where n is the number of folds, and 0.05 is the thickness of the paper before we start folding. 0.05 millimeters. Use graphing technology to graph the equation T equals 0.05 times 2 to the n power. Okay, so here I have graphed in our graphing calculator. We have 0.05 times 2 to the x power. And if we graph, we can clearly see that it's increasing, right? Because as we fold paper, it's getting thicker and thicker. Now we can answer the questions. How many folds does it take before the folded sheet of paper is more than 1 millimeter thick? How many folds before it is more than 1 centimeter thick? Explain how you know. So let's keep in mind that the units did change. We went from millimeters to centimeters. We know that there are 10 millimeters in 1 centimeter. Let's keep that in mind. So how can we answer this question? Well, we could zoom in, we could trace. I prefer to go to the table. So here we can see that as soon as we get to 4 folds, we're just below 1 whole millimeter thick. And once you get to the 5th fold, you are over 1 millimeter thick. You're now 1.6. So that's the answer. 5 folds gives us 1.6 millimeters thick paper. And let's find out. So what we're looking for now, because they want to know when the paper is 1 centimeter thick, we can think of that as 10 millimeters thick. 10 millimeters. So I'm going to go down until y exceeds 10 millimeters. Here it is, 12.8. So the 8th fold gives us 12.8 millimeters, also known as 1.28 centimeter thick paper. Number 2, the area of a sheet of paper is 93.5 square inches. Find the remaining visible area of the sheet of paper after it is folded in half once, twice, and 3 times. So once again, I'm organizing by a table. Here are the number of folds, and here's the area. So at 0 folds, or in other words, at the very beginning, the paper is 93.5 square inches, right? So 0 goes with 93.5. Now after 1 fold, since it's getting folded in half, we can simply take 93.5 and divide it by 2. 46.75. Let's fold it 2 times, divide it by 2 again. 23.375, and then we'll fold it a total of 3 times. So we'll divide it by 2 again, divide it by 2 again. And we get 11.6875. So as you can see, it's getting halved, half each time. Letter B, write an equation expressing the visible area of the sheet of paper in terms of the number of times it has been folded. So here we realize that the initial area is 93.5. So they tell us what to use. We're going to use A. So we have A equals 93.5, and the decay factor is 1/2 to the n power, because n is the number of folds. Use graphing technology to graph the equation. So here we have in the calculator. That's what it looks like, right? We're folding the paper in half, so it's decreasing, right? The area of the paper is decreasing exponentially. Now we can answer the questions. In this context, can n take negative values? Explain your reasoning. Can the number of folds ever become negative? And not in this situation, unless the original paper can be unfolded. But they never said anything about the original paper being already folded. So we will assume that it's just plain one layer of paper, 93.5 square inches. So it cannot be unfolded, can't be negative. Letter E, can A take negative values? In other words, can the area ever be negative? Now, if you keep folding paper in half and half and half and half, can that paper disappear and then become negative? Of course not. So the answer would be the area of folded paper can never be negative. Okay, let's take a look at the practice problems. Number 1, the number of people with the flu during an epidemic is a function f of the number of days d since the epidemic began. So you have to think to yourself, the number of people is a function, that's the output. F is the symbol that represents the output, the number of people with the flu. And the input is the number of days since the epidemic began. Okay, so remember, we're thinking functions, input, output. So here's the equation, and answer the following questions. Now letter C, I'm giving you a hint here. What does f of 1 mean in this situation? Well, fill in the blank. The number of people with the flu blank days after the epidemic began. Blank days after the epidemic began. Number 2, the function f gives the dollar value. Gives means output of a bond t years after the bond was purchased. So the number of years is the input. So once again, you're going to answer these questions very carefully. If you need to, go review your previous lesson all about functions before we got to the exponential unit. So we have f of 0, f of 4.5, and then here f of t, you have to find out the input given the output. Number 3, now because it says technology required, I will do the questions that require the technology, but you can answer the other ones. A function f gives the number of stray cats in a town t years since the town started an animal control program. The program includes both sterilizing stray cats and finding homes to adopt them. An equation representing f is f of t equals 243 times 1/3 to the t power. What is the value of f of t when t is 0? You can answer that, no problem. What is the value of f of t when t is 1/2? Explain what this means in this situation. So we have f of 1/2 is approximately 140. Now I did this on the calculator, and it's the number of stray cats remaining after 6 months of the program. What does the number 1/3 tell you about the stray cat population? You can answer that. And for letter D, use technology to graph f for values of t between 0 and 4. What graphing window allows you to see values of f of t that correspond to these values of t? So here I've used my graphing calculator to graph this equation. We end up with this looking graph. We don't see all of it. So we should realize that yes, the cat population is being controlled, they're being adopted, and so it's decreasing. I want to see the initial value of cats. I know that's going to be 243, so I'm going to go to my window and I'm going to adjust my y max to 243. I'm never going to have negative cats, so I'm going to go back to 0 for there. And for the x-min, x-max, they give us what they want. It's right here. Use graphing technology for the values of t between 0 and 4. So my x-min is 0, my x-max is 4. Let's graph this. And now we can see the entire graph. It's all in quadrant 1, and that's why these are the window settings. 0, 4, 0, 2, 43 for the X min, X max, Y min, Y max. Number 4. Again, I've sketched the graph for you, and now you can answer the question better for using the graph to answer letter C. And last page of the homework of the practice problems, number 5, the dollar value of a moped is a function of the number of years t since the moped was purchased. So here's the equation. As you can see, it is decreasing, right? Just like a car, as soon as you buy it, it starts to depreciate. What is the best choice of the domain for the function f? My hint for you here is it is decreasing in value, and when it gets down close to no value at all, that'll sort of tell you if you need to go down to 10 or go up to 10 years or up to 100 years of depreciation. What makes most sense? Finally, number 6. This one is a blast from the past. It's from Unit 5, Lesson 4. So I've gone ahead and helped you out by completing the first 2 values of the table. At 0, we have 1,000 milligrams of medicine left in the body, and after 1 hour, it's been diminished, and we're left with 800. Now, excuse me, I made a little mistake here because it says each hour 1/5 of the medicine in the patient's body decays, 1/5 decays, so 1 minus 1/5 is 4/5, and that's why 4/5 should be our factor of change. Good luck to you.